students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, as you all know, we have started this series where we are covering every concept of chemistry. So yes, today we are going to start a very important as well as interesting and a very scoring topic, that is your coordination chemistry. Okay, so this is the first lecture on coordination chemistry. So today we'll be covering the topics Werner's theory and some important definitions. Okay, so this is not a very long video, but yes, questions have been asked from Werner's theory. Many questions have been asked in the previous year. So yes, it is important to understand this. Okay, so now coming to another important here, please join our WhatsApp channel. It is very important because whatever notes, whatever class notes you want, that will be available in our WhatsApp channel. The question paper, the solutions, everything will be provided in the WhatsApp channel. Okay, so that is why please join the WhatsApp channel, and the link of the WhatsApp channel will be there in the description section of this video. Okay, so yes, now sit with the notebook and a pen and let us start the first lecture of coordination chemistry, which is very easy, very scoring as well as very interesting. Okay, so now coming to how, as I tell you every chapter, how are we going to cover this topic. So there will be again 4 parts here. Okay, so in the first part I have Werner's theory and important definitions. Okay, so we are doing this chapter from the perspective of KCET. Okay, how can you crack KCET exam? So we will not be focusing more on like writing definitions and all. I will explain every concept and we will apply this concept in every questions. Okay, so next in part 2 it is nomenclature and isomerism. Okay, very important. Nomenclature is the most important topic, very important topic. Werner's theory, very important topic. Okay, next coming to part 3, we will be talking about bonding theory, the most again very important topic, and then in part 4 we will be talking about metal carbonyls and application. Okay, which is not very important, but yes, some questions have been asked previous years also. But the most important topics are your metal nomenclature, isomerism, bonding theories and Werner's theory. Okay, but important definitions, if you do not understand, then you cannot solve any of these questions. Okay, so now coming to year-wise weightage. So every year you can expect 3 to 4 questions from this chapter. Okay, a high weightage topic, as well as the most important thing is it is a very scoring topic. You need not do very much effort to understand, very easily understandable, easily you can nothing to memorize, everything is concept based. The only thing you need to remember is the D block electronic configuration. Okay, fine. So you can see in 2024 there were 3 questions, 2023 2 questions, 2022, 2021 3 questions, here 4, 1. So almost you can expect 3 to 4 questions every year. Okay, now coming to coordination chemistry, today's topic, that is Werner's theory and important definitions we are going to cover. Okay, now first coming to coordination compound. What is this word called as coordination compound? What does that mean? Okay, when someone asks you what is coordination, we have studied ionic compounds, we have heard about covalent compounds, right? But then what is this coordination compound? So easily you have to understand 2 things in a coordination compound. Metals will be there. Which metals? Transition metals. Okay, transition metals will be there. So that is why first we studied transition metals chapter, we completed, so that you can understand these basics of coordination chemistry, right? So if you have remembered, in transition metals we have learnt a property that transition metals can form complex compounds, right? And the reason for that was their availability of d orbital, high ionic charges and variable oxidation states, right? Similarly, this is the compound. Transition metals have these properties because of which they can form coordination compound. Now what is coordination compound? Let us see. Now so there will be metal atom. Metal atoms will bind with either neutral or negatively charged molecules. Either neutral or negatively charged molecules. These neutral or negatively charged molecules are called as ligands. Okay, so there will be metal and there will be ligand. Now between these two, what type of bond is present? Coordinate bond is present. Okay, we have heard ionic bond, covalent bond, and there's one more type of bond, that is coordinate bond. So because there is coordinate bond between these metal and ligands, we call them as coordination compounds. Now question may arise, ma'am, what is coordination or coordinate bonds? Now I'll explain you with very simple example. Okay, one real life example we'll take. Suppose there are two students, A and B. Okay, now you have been given, your teacher gave you a project, okay, and the teacher told that the project should be in such a way that you have to write something, the content should be in one color and the headings should be in another color. Okay, now what happens, suppose A has blue pen, okay, and B has black pen. Only one pen they have, right? This is having blue pen and this is having black pen. So now they decided how can they share and do the project. So what A and B decided that, okay, first I will write the content in blue pen. I'll write the content in blue pen and you write the content in black pen. After writing the contents, what we can do, we will exchange. Okay, we'll exchange our pens and then I will write the headings and you will write the headings in different pens. Right. So now you see, when the project came to the teacher cannot know that, okay, one child has only one pen and another child has only one pen and they have shared it. It is not like that. When the teacher sees the project, she can easily understand, okay, they have done correctly the project. But what A and B has done, they have done sharing, right? Both have shared one pen and they have completed the task. So when in a bond, when both the atoms give electrons and form a bond, that type of bond is called as covalent bond, which we all have known in our previous classes. Now what is coordinate bond? We'll understand it here. Same example we'll take. Now what is happening here? See, A is not having any pen. Okay, A is having 0 pen and B is having both blue and black pen. Okay, B is having both blue and black pen. Now what does they do? B says to A, okay, do not worry, you are my very good friend, I will help you. So what I'll do, you take this pen, okay, you write it, then after that you take this pen and complete your project. So what is blue, this B doing? B has given one pen to A, okay, and then again they have shared both the pens, right, and then the project is being completed. So now the same thing, if there is a bond between A and B, okay, and both the electrons of this bond are given by B, then we call it a coordinate bond. Are you getting? Generally, when a bond is formed, one electron should come from A, one electron should come from B, and a bond is formed. But if certain cases the electrons are given by a single element, then we call it as a coordinate bond. Now in this metal to ligand, what happens? Both the electrons in this bond are given by the ligands. Okay, so that is why ligands should be either neutral or should be negatively charged. They should have electrons. If ligands are positively charged, means they are electron deficient, so they cannot form the coordinate bond, right? So that is why ligand should be either neutral or it should be negatively charged. Now see, this example you can see here, platinum. Platinum is a transition metal, right? So these are your ligands, okay. OH2 is a neutral ligand, right, and chlorine, if you remember, chlorine charge is -1, so this is a negative ligand, right, and this bond which you can see here is a coordinate bond. Okay, so here who is giving electrons? Oxygen is giving electrons, here chlorine is giving electrons. Okay, fine. Now coming to the most important topic, that is Werner's theory. Okay, so Werner's theory says that in a coordination compound, okay, so how do we represent coordination compounds? Coordination compound is like this. Suppose I'll take this example. Okay, so coordination compounds, you might think, how does it look? It looks like this. NH34Cl2. Okay, so this is an example of coordination compound. We will study that in detail. But first let us understand what is Werner's theory. Now Werner's theory tells that in a coordination compound, this metal has two types of valencies. Okay, what are these valencies? Primary valencies and secondary valencies. Okay, in a coordination compound, the metal has two type of valencies, that is primary valency and secondary valency. Now, what is primary valencies? The primary valencies are those which are ionizable. Now see, if you dissolve this compound in water, okay, what will happen? This complex will form one ion and this one will form another ion. This complex will not break. Complex itself will come out as one ion. So what I can get? I'll get Pt NH3 whole 4, okay, 2 plus as one ion, and there will be two chlorine ions. Okay, so now this one which you see, this primary valency are normally ionizable. Okay, so this 2 plus, these ions are your primary valencies. Okay, and they are ionizable, means when you put it in water they can ionize and are generally negative ions. Okay, so you can see these ions, this is your primary valence. So plus 2 of platinum is your primary valency and it is ionizable, and this plus 2 is satisfied by negative ions. Okay, once again I'll tell 3 points. Primary valency are those which are ionizable. Okay, the charge of the complex, this charge of the complex is called as the primary valency. Okay, now this is ionizable and this charge is satisfied by generally negative ions. Okay, now if you see, secondary valencies are non-ionizable. So for platinum, this NH3 okay, this is the secondary valency. Okay, are non-ionizable and satisfied by neutral molecules or negative ions. Now the secondary valency is equal to the coordination number and is fixed for a metal. Now what is coordination number? So how many the metal binds to how many ligands, that is called the coordination number, and that is the secondary valency of the metal. So here I can say the secondary valency of the metal is 4, right? Okay, now coming to, now this secondary valencies, okay, how these 4 ligands are attached to the metal, that decides the geometry of the molecule. Okay, once again let us revise. The metal which is present in a coordination compound has two valencies. One is your primary valencies, another is secondary valency. Okay, now the primary valency is the one which is ionizable and is satisfied by negative ions. Secondary valency is one where the it is non-ionizable and it is satisfied by both negative and neutral ligands. Now the secondary valency is equal to the coordination number of the metal. What is coordination number? The number of ligands that is attached to a metal is called as the coordination number. Okay, now if we see this one, okay, now if we see example here, see, this is a question from NCERT, but very easy and a very good example to understand primary and secondary. Now see, what happens is it is saying that the moles of AgCl precipitated per mole of the compound with excess of AgNO3. Now when you reacted this compound with AgNO3, 2 moles of AgCl is produced. That means that 2 moles of AgCl is produced means 2 chlorine should be outside the complex. Then what will be the complex structure here? 2 chlorine I have to keep outside. So Pd, and there will be 4 NH3, okay, and then 2 chlorine should be outside. If this is there, then when this will ionize, 2 chlorines you will get as a product, and that will react with AgNO3 to give you 2 AgCl. Okay, now you have to find the secondary valency. So what is the coordination number of Pd? How many bonds, how many ligands are there? 4. So the secondary valency here will be 4. Now if you see here, 2 molecules again is formed, so 2 chlorine will be outside. So I can write NiH2O whole 6 and 2 chlorines, right? Now you see how many ligands are attached here? 6. So here it is, the secondary valency will be 6. Now see, PtCl4 is there, okay, PtCl4 is there, so that means there is no there is secondary valency, there is no AgCl formed, so all the chlorines will be inside. So I can write the compound like this. Okay, then the secondary valency here will be 4. Now if you see COCl3 4NH3, only 1 chlorine will be outside because only 1 AgCl is formed, right? So I can write only 1 chlorine outside here, CO, and there is 4NH3, okay, and then 1 chlorine inside, sorry, 2 chlorine inside and 1 chlorine outside. So now if you see how many ligands are there, 4 NH3 and 2 chlorine, so the secondary valency here will be 6. Okay. Now if you go to PtCl2 NH3, So here there is 0, that means all the chlorines are inside. So I will get PtCl2 NH3 whole 2. Okay. So if you see here again, because there is 0, so everything will be inside, secondary valency here will be 4, right. So how many moles of AgCl is formed, that many chlorine you have to keep outside. If 0 AgCl is formed, then no chlorine will be outside, all chlorines will come inside, okay, and then we can calculate the secondary valency. Clear? Okay, next, the number of ions given by K2, okay, so this is like this, K2 PtCl6, okay. So if you see, how will it dissociate? It will dissociate as 2K plus and 1 PtCl6 2 minus, right. So now if you see how many will get, this is 2 ion and this is 1 ion, so total 3 ions, right. Correct answer is 3. Now coming to which will not give the usual test for iron. So if you see here, the iron is present inside the compound, right, so it will not react with the reagents. So this cannot give the test, so the correct answer here is option number C. Okay. Now let us understand the important definitions here. So I will not give any definitions and all, but I will explain every term here. Okay. So there are these things that you should know: coordination entity, central atom, ligands, coordination number, oxidation number, homoleptic and heteroleptic complexes. Okay. We will be discussing these terms. So these 4 terms I can explain you within a one diagram. Okay. So this is that diagram. See. So here it is already marked. This one which is present in the square brackets, okay, this is called as coordination sphere, or we call it as coordination entity. Okay, this square bracket is called as, this much term, this whole thing is called as coordination sphere or coordination entity. Now whatever other atoms are present apart from this coordination entity is called as counter ion. Okay, so K4 is the counter ion. Now in this coordination sphere, there is one central atom, that is your transition metal, and there will be some ligands, that is that can be negatively charged or neutral ligands. Okay. So now how many ligands are there? That is your coordination number, or we can say this is also secondary valency. Okay, secondary valency. Now next one, you also need to calculate the oxidation number of metal. Oxidation number of metal. How to calculate that? See, you have to calculate, see, just how do we calculate oxidation number in reduction reaction, in redox reaction, same thing, but you need to know the charge of the ligands. Okay, that I will tell you. For this particular exam we will solve it. See, so there is potassium, each potassium charge is +1, so there is 4 potassium, so 4, okay, plus Fe, we want to calculate the oxidation number of Fe, so let it be X, plus Cn. For this I am telling you, Cn has -1 charge. Okay, Cn has -1 charge. So I can write, there are 6 Cn, so I can write -6 is equal to 0, right? There is no net charge here, equal to 0. So what will be X equal to? +2, right? So this +2 is the oxidation number of Fe here. Getting? So what is oxidation number? Oxidation number is the charge of the metal in the complex. Okay, that is the oxidation number. Clear? All the terms are clear. First, coordination entity, that is what is the total thing present in the square bracket is called as coordination entity or coordination sphere. The metal present here is called as the central atom. The other atoms that is the presence are called as the ligands. Then you have the ions apart from the coordination sphere is called as counter ion, and the number of ligands present is called as coordination number. Okay, then you have the oxidation number of the metal also, you need to know how to calculate. For that, what you need to know? The charge of the ligand. So I will give you a list of ligands and their charges in the next class when we will be doing, so that you can easily calculate the ligands charges. Okay, fine. Now coming to ligands. So about ligands, we are going to study these 3 things. One is denticity, one is ambidentate ligands, and another is chelating ligands. See, now what is denticity? Metal is there, okay, metal is there, and then ligand is there. So if the ligand binds to the metal, okay, by only single atom, for example, metal is there and we have the ligand chlorine. Okay, metal is there and we have the ligand chlorine. So in that case, if metal is there and we have the ligand chlorine, chlorine is binding through only one atom, that is called unidentate ligand. these type of ligands will be called as unidentate ligand. Now suppose there is one metal and a ligand is there, but it has two sides from where it can bind to the metal. Okay, so such ligands are called as bidentate ligands. One example for this one is your NH2, CH2, CH2, NH2. So what happens here? In this type of ligand, there are two sides from where it can bind to the metal at the same time. Okay, both the parts will react, both the donor site will form bond with the metal. Okay, so the number of atoms, the number of groups from which the metal can bind, the ligand can bind to the metal is called as denticity. The number of groups by which the ligand can bind to the metal is called as denticity. So here it is binding only through one group, or I can say one atom, so it is unidentate. Here from two sides it is called bidentate, right? If there is one another ligand is there, suppose this one, NH2, okay, NH2, CH2, CH, then I have NH, again CH, 2CH, NH2. Okay, so here this nitrogen and this nitrogen, right? So these are three donating sides. So if metal is present here, if this is the metal, then they will bind to the metal from three sides. Such ligands are called as tridentate ligands. Getting? Okay, now the maximum denticity that we have seen is your hexadentate ligand. So I'll show you the example here. So you can see this is the example of a hexadentate ligand. You can see there is 2 nitrogen atoms and there are 4 oxygen atoms. So these together bind to the metal at the same time. So what is the denticity here? The denticity here is hexadentate. I hope this is clear. What is denticity? Number of atoms by which the ligand bind to the metal at the same time. Okay, now there is something called as ambidentate ligand. Okay, so ambidentate ligand means, see here, if the metal, okay, has more than 2 donation sites but only one binds at one time. If the metal, remember, very carefully understand, if a ligand has 2 donation sites, I can donate from here, I can donate from here, 2 donating sites are there, but at a time only one will donate. If this one is donating, this one will not donate. If this one is donating, this one will not donate. Such type of ligands are called as ambidentate ligands. Your question may be arising, ma'am, what is then bidentate ligands? Bidentate means 2 donating sites are there. Okay, this is the metal. Okay, so let me show you. Suppose this is the metal and 2 donating sites are there. Okay, these 2 are the donating sites. Now both the donating sites are binding at the same time. That is called bidentate ligands. Ambidentate ligands means if this one is binding, this one will not bind. If this one is binding, this one will not bind. But 2 donating sites are there, but at a time only one will bind. Okay, so now you can see the example here. Wait. Okay, now if you can see the examples here for NO2. Okay, so NO2 is a metal like that. It has nitrogen as a donating site, oxygen also as a donating site. So oxygen can bind. So when oxygen is binding, nitrogen is not binding, or nitrogen can bind. See, nitrogen can bind. So if nitrogen is binding, oxygen is not binding here. Similarly, one example of SCN is there. In SCN, if S is binding, we call it thiocyanato S. But if N is binding, then we call thiocyanato N. Okay, so yes, here also, but when S is binding, N is not binding. When N is binding, S is not binding. So 2 donating sites are there, but at a time only one will bind. That is called as ambidentate ligands. Okay, now what is chelating ligands? So now you see here, chelating ligands is when there is more than one donor sites. Okay, like for example, if you see NH2, CH2, CH2, NH2. More than one donating sites, this one will also donate, this one will also donate. Metal is here. So when they will bind at the same time, this is a bidentate ligand. So they are forming a circular, or I can say cyclic compound. A cyclic ring is formed. So those ligands which can form a cyclic ring with a metal is called as the chelating ligand. Okay. So what is there? Let us just write down them in very short. Denticity, number of donating sites, which bind at the same time, right? Ambidentate, 2 donating sites 2 donating sites, but one at a time. Okay. Chelating ligands means that forms cyclic ring with the metals, right? So now, leaving the monodentate, bidentate, tridentate, tetradentate, hexadentate, everyone will give you a chelating ligand. Everyone will form a cyclic ring. Okay. Now you must remember this ligand, that is EDTA. I forgot to tell you name. EDTA ligand hexadentate. Okay. Very important ligand. It has 6 donation sites, and all the 6 will bind at the same time. Okay. Fine. So now let us questions. Diethylene triamine is. So diethylene triamine. So if I draw the structure here like this, NH2, CH2, CH, NH2, sorry, NH, CH2, CH, NH2. Okay. CH2, NH2, CH2, NH2. Yeah. So this is the structure of diethyl triamine. Okay. So how many donation sites are here? This one will donate, this one will donate, and this one will donate. 3 donating sites are there. So it will behave as a tridentate ligand. Okay. So if metal is present, then all the 3 will bind at the same time. Okay. We call it a tridentate ligand. Okay. Next, if SCN is a ligand, okay, SCN is a ligand, and N is attached to the metal, so it is like this, then the ligand name is, so if N is attached, we call it thiocyanato N. Okay, just now I told you, if S will bind, we call it thiocyanato S. Okay. Next, EDTA is a, just now we discussed EDTA structure. EDTA is a hexadentate ligand. Okay. So there is 4 oxygens and 2 nitrogen sites are present. Okay. Next, the coordination number of cobalt in this structure. Okay. So En, I'll tell you what is En. En is this type of ligand. NH2, CH2, CH2, NH2. Okay. So now you see, cobalt coordination number means how many ligands are there. So there is 2 bromines, right, and there is 2 En. Okay. You might think coordination number is 4, but you are wrong here. Very, very carefully see, from En, from one En there are 2 sides, right. So if I draw here, see, metal is here, so this is N, this is one En, then this is another En, and then I have 2 bromines, right. So how many bonds the metal is forming here? 6 bonds are there, right. So the coordination number is not 4, rather it is 6. Okay. So you have to be very careful when you see some bidentate or tridentate ligands. Okay. Fine. Next, how many EDTA molecules are required to form an octahedral complex with Ca2+? Now, octahedral complex means the coordination number should be 6. So, metals when form 6 bonds, okay, I'll draw like this. So, metals when form 6 bonds, it is called as octahedral. And if you remember EDTA, one EDTA, it is a hexadentate ligand. That means what? It has 6 sites, right. So from the 6 sites, it can form bond with this. So with one EDTA, all these 6 sites can be occupied. All these 6 bonds can be formed with one EDTA. So to form one octahedral complex with Ca2+, we need only one EDTA. Okay. Okay. Now my question is, how many En molecules are required to form an octahedral complex? How many En molecules are required to form an octahedral complex with one Ca2+? You have to answer this in the comment section. Okay. En to form, how many En is needed, and how many triethyl amines? This one. Diethyl triamine. How many diethyl triamine is required? Diethyl triamine is required to form one octahedral complex with Ca2 plus, and how many ethylene diamine is required to form? So I need two answers in the comment sections. Okay, I want everyone to write correctly. Okay, next understanding the next definition, homoleptic and heteroleptic. This is very simple. See, if the ligands are, see here all the 6 ligands are of one type, that is NH3. If all the ligands are of same types, then we call it homoleptic. Okay, so what is mean by homoleptic? All the ligands are same. All the ligands are same. Now heteroleptic means what? If the ligands are different. You see 4 NH3 is present and 2 chlorine is present. That means the ligands are different here. So this type of, when ligands are different, we call it heteroleptic. Okay, that means different ligands will be present. Different ligands are present. Okay, fine. Now we will be practicing some questions. Okay, so first is your, in the DNF block I gave you a homework question. Okay, so I hope all of you have solved this. Which of the following lanthanide ions is paramagnetic? So for paramagnetic we need unpaired electrons, right? So now let's time to practice. Okay, which of the following lanthanide ion is paramagnetic? So this is the homework question that I gave you in my previous class, right? So if you have done the electronic configuration, Eu2 plus will have unpaired electrons, and that's why that is the paramagnetic. Okay, now let us do our question today. The complex hexaamine platinum 4 chloride will give dash number of ions on ionization. So this one you can do if you have learned the nomenclature part. Okay, but do not worry, what I'll do is I'll give you the structure, then you have to think the answer. Okay, when we study nomenclature, then you yourself can draw the structure. Now I'll draw for you. So hexaamine platinum, so there is platinum and then hexaamine, so hexaamine platinum 4 and then chloride is there. Okay, this is the structure. So now tell me, if I put this in water, how many ions I'll get? So if you put this in water, what will happen? This complex itself will be 1 ion. Okay, this complex itself will be 1 ion, and I have 4 Cl minus. Okay, there will be 4 Cl minus. So the total number of ions I'll get is 4 here and 1 here, that is 5. Correct answer is 5 here. Okay, next, see, addition of excess of AgNO3 to aqueous solution of 1 mole of PdCl2,4NH3, PdCl2.4NH3, okay, give 2 moles of AgCl. So 2 moles of AgCl is produced, that means 2 chlorine should be outside. Then if I put 2 chlorine outside, then what I'll get? PdNH3,4Cl2. So PD, and there should be 2. Okay, 1 second. So there has to be 2 chlorine outside, right? So I'll write again PD, then we have NH3 whole 4 and we have Cl2. Okay, so now you see, so we will get this one. This is the structure of the compound. Now if you put it in water, then what I'll get? PdNH3,4, okay, and then I'll get 2 chlorines, right? So there is 1 cation and there is 2 anions, right? So 1 cation, there is 1 cation and we have 2 anions. So the type of electrolyte, okay, the conductivity of this solution corresponds to which type of electrolyte it is? 1,2 type of electrolyte. Okay, the correct answer for this question will be option number 3. Number of cations, ratio number of anions. Okay. Next, homoleptic complex among the following. So you know homoleptic means all the ligands should be same. So here all the ligands are C2O4. Here also all the ligands are OH4. So 1 and 3 only. Okay, here this is chlorine is there, En is there. So these are 2 different types of ligands. So it is heteroleptic complex. Okay, so we will get 1 and 3. Next, the coordination number of Fe and cobalt in the complex ions and are. So we need to find the coordination number of Fe and cobalt. So see, C2O4 again is a bidentate ligand. If you see Fe C2O4, it is like this. C2, okay, O4. So like this we have 3 3 it is there. I am just writing like this. Okay, so 3C2O4. Okay, so this is carbon. Okay, so now you see how many bonds the ligand is metal is forming. So 6 bonds are formed here. So for iron the coordination number is 6. So we can eliminate these two options. Next, SCN. SCN, you know, it is a monodentate ligand, right? So only one atom forms a bond. So here cobalt forms 4 bond with SCN. It is like this. Okay, so here how many bonds are formed? 4 bonds are formed. So here the coordination number is 4. Correct answer is option number C. Okay. Next and the last question, the coordination number and the oxidation state of the element M in the complex NO2. Okay, this is the complex and you need to find the coordination number and the oxidation state. Okay, so first let us try to find the coordination number. So if you see, I'll draw the structure here. M, there is 2 En, right? So En I showed you like this, it forms bond. Okay, 2 En is there, and then we have C2O4. So I'm just drawing it like this. Okay, so now what is the coordination number? The coordination number is again 6, so we can eliminate these two options, right? Then the oxidation number of the metal. So if you see now, okay, M, okay, let the oxidation state of this one is M. En has 0 charge. Okay, I'll tell you when we study the nomenclature, I'll tell you all the ligands and their charge. For now, understand En is having 0 charge. So 0 into 2, 0. C2O4 is having 2 minus charge. So there is 1 C2O4, so that is minus 2, and NO2 charge is minus 1, right? So I'll get this as X is equal to plus 3, right? 6 and plus 3. So the correct answer is option number C. Okay. Okay, so next we have, okay, so this is done. Okay, now this question is for you. How many ions per molecule are produced in the solution when the more salt is dissolved in excess of water? Okay, so try this question, and if you are not able to do, I'll explain it in the next class. Okay, so yes students, this was a small introductory class for coordination compounds. Next lecture is going to be very, very important as well as very interesting, because we are going to do nomenclature and isomerization in the next lecture. Okay, so I hope you have understood these all things, and please comment down your answers. And if you are liking this series, if you are following with me, if you are studying with me every day, then stay tuned for the next class, and please subscribe the channel, and also keep preparing, keep making notes, and all the very best for your KCET 2025 preparation. Remember, we have to hit that 60 score. Okay, thank you and see you soon in the next class.